Right. Think. Welcome to Q&A Friday. It's Friday, so hopefully everybody out there had a great week this week. I know I did. I was with a great bunch of individuals teaching some NFPA 70E safe work practices. So if you're out there watching, thanks for all you guys do and gals do. So we had a great week talking about 70E this week. All right, so today is Q&A Friday, and we started this last week, if you recall. So I want to continue that, and I've got a hard stop at 1 o'clock, which I don't believe I have my call-in information for that one. Okay, so let's talk about some questions. I just did some. What I'm going to do is go out to the YouTube channel because that's where things typically come in on, and we're going to look at some of the questions. Okay, let's take the first one, which was about a week ago. JW said, it is less likely you would be working on energized medium voltage equipment, but the definition of de-energized is quite different in that you have to ground it and have all the concerns about induced voltages static from T lines or contact with other lines somewhere up or downstream. All right, so JW, thanks for the note. What I'm going to take a look at 70E. I've got the 2021 version here, and I'm coming off of a week of 70E. So I have a pet peeve already. We've got to, I think, in my opinion, and I think this is very much in line with JW's comment. Hey, Nihad, good to see you, brother. I think this is very much in line with JW's comment, but he uses the term de-energized, and I'm going to ask everybody to try to refrain from using that word. And here's why. We don't just de-energize. We don't just, I think it sends the wrong message. And the reason I say that, you think about this, usually they'll say, hey, don't work hot, work de-energized, turn it off. But that's not what we're really doing. I mean, we are, but it doesn't really tell you everything, because to JW's point, there are other things. And he says the definition of de-energized. Where is the definition of de-energized? It's not in there. Exactly, JW. It's an electrically safe work condition. Because to your point, you're saying that you have to ground it. Yeah, but you have to block and tag it out. You've got to test for absence of voltage. And the test for absence of voltage is energized work. If you think about it, you have to dress for the PPE. You have to have the proper PPE. You can't assume that it is actually in an electrically safe working condition until you verify it. And you have to assume that it is not in an electrically safe work condition. And that's the challenge on all of this, whether it be medium voltage or low voltage. When you have high incident energy values and you have to dress for it, if it's so high that you can't dress for it, then you have to have other methods to verify. And some of those might be remote hot sticks and things of that nature to get you out of the electrical safe work or the electrical arc flash boundaries and whatnot. So it's really important. And I agree with you. There are other things that need to happen in whether it's medium voltage or not. Even on low voltage assemblies, we'll still do some of the same practices, very similar practices. So very good point. I appreciate that one. JW again, there's a reason to be hesitant on giving scope of systems over 35,000 amps over to the NESC. That's the National Electrical Safety Code. A lot of the rules in the NESC are written for utilities who have much more rigorous employee training and equipment inspection maintenance of their gear. Utilities operate electrical systems. Customers own these. They aren't necessarily doing maintenance full time on their equipment. All right, so um, I agree with you, JW. And I would say medium voltage period. Here's the challenge, and here's why in my opinion, the National Electrical Code includes medium voltage requirements. What is the scope of the National Electrical Code? The scope, or who has to follow the National Electrical Code, who doesn't? The National Electrical Code does not apply to utility-owned installations. That is the NESC. But to JW's point, the utilities they work in that on a daily basis, right? They are maintaining their systems, they're following their rules, their policies, their procedures, and they're very highly trained and highly skilled in those applications, all the ways up through whatever it is, the voltage transmission lines, 138 kV, whatever it is. Now, medium voltage is also being used in campus-wide environments, in industrial facilities, customer-owned applications, and dealing with medium voltage applications is different, and it demands and expects a qualified person, right? So in my my week of 70E this week, we talked about the qualified person, and we had as a team, a level of recognition that in many cases, when we talk about the qualified person and 70E, we're talking about the person who understands how to recognize how to recognize shock hazards, how to do a shock risk assessment, an arc flash risk assessment. We're talking severity and likelihood a lot, the tools, etc. But a big part of electrical safe work practices from a qualified person perspective is understanding the equipment that you're working on. If you work on low voltage assembly, say it's panel boards and switchboards, and you don't get into switchgear, you don't get into medium voltage applications, the equipment in that equipment, the components inside of the equipment, the relays, there will be CTs, PTs, there will be all of these other control type of equipment that you have to understand. There might be a UPS inside of there, inside of that big gray box that you may not find in a switchboard, and you probably aren't going to find in a panel board for sure. That even though you turn the power off, you still have voltage there. Now that voltage could be 48 volt DC, it could be 120 volts, it could be 480 volts. You don't know what that alternative power supply is there for, what it is doing, and why it needs to be there if you lose power. It might be there for relay operations, contactors, etc. The more complicated the assembly, the more of a challenge it is for the electrical worker to understand the hazards, right? We teach people in 70E, when we talk about safe work practices, we teach them what shock is. We teach that above 50 volts, we talk about the shock risk analysis and understanding the shock hazards and recognizing shock hazards, how to test for absence of voltage. But if that individual doesn't understand everything that needs to be tested for absence of voltage in a specific piece of equipment, then you may be really, really good at testing for absence of voltage, but you didn't test everything you needed to test, and there still might be energized components within that assembly because you don't quite understand, or you're not as familiar with the equipment and all that it brings to the table. So medium voltage is similar in that there's a lot of stuff out there, a lot of ancillary components within, whether it be the equipment in the substation, etc., that you need to think about and put a different thinking cap on and be educated and trained on that equipment. And when you take that medium voltage equipment and you put it into a commercial environment, customer owned environment, they They may have the right contracts in place with the qualified people who are going to maintain that equipment appropriately, and perform all of the calculations that are needed, et cetera, over the life of the installation. But in many cases, they don't. That's not happening. And when you think about the installation, the NESC has a level of awareness of the person who's going to be working on it. So the requirements in the NESC might not be what you would see in the NEC because of the level of expertise in and around that's always around that equipment. So I think your point, I agree with your point, JW. You pointed out that that the utilities have much more rigorous employee training and equipment inspection and maintenance of their gear. And I think I would emphasize the training more so than the maintenance. I mean, I believe they would do maintenance, et cetera, but every facility should be doing maintenance on their equipment, regardless of the voltage levels, medium voltage, low voltage, in its entirety, and that's critical for 70E. But the training, I mean, the qualified person is really critical. And in my opinion, the 7 NESC may have requirements that anticipates that qualified person being there that you can't anticipate on the commercial side of the business. So, and that's just my opinion. But I'll tell you what, though, the 2023 code cycle is making changes. They are looking at medium voltage. It's controversial. There's people who are on both sides of the coin there. Whether some people like it, some people don't, and some people say proceed cautiously. And I would say you always have to proceed cautiously. But I think from what I've seen so far, I can't find the negative aspects of where they're going. They're putting the focus on medium voltage, and I think that's important. Okay, Pierre Belarge, I'm not sure, Belarge, Belarge. 1 week ago, where and when did it become the NFPA 70, that's the National Electrical Code, choice to decide what homeowners get to install to control the lighting? What about the cost? To boot, no quote unquote power switches to be installed. I am sorry, Thomas. I like you a lot, but the NEC NFPA is going too far, too fast in making these decisions. You all need to slow down. Might I remind all of you, 90.A, why not have the manufacturers actually install this type of control in a protocol type house, open it to the public, and let them help in deciding this gigantic decision? Very poor choice, in my opinion, and I have only been at this for 40 years, only for 40 years, out of control, becoming decision makers for the public. I am stunned by this section change and others over the last number of cycles. Ooh, now we got to find out what section Pierre commented on. So let me take a look. Where is his comment? Pierre Belarge. Oh, 210.70. I get my book. Oh, ow. I hit my hand. Tamaki Ono, thanks for joining. I'm going to be looking up 210.70 here. All right, so 210.70. He's pretty upset about 210.70. I'm curious what, I don't think we made a big change in 210.70. I mean, this is my code panel. Not that I do not speak on the behalf of Code Making Panel 2. I do not speak on behalf of NFPA. I just want to set that clear. Although I am on Code Panel 2, whatever I say in this regard is my opinion and my opinion only. Okay, so 210.70. Let's see what changes we did in 210.70. Lighting outlets required. Okay, lighting outlets shall be installed where specified in A, B, and C. A is dwelling units. We didn't make any changes there. Oh, well, wait, hold on. In the parent text, A1, habitable rooms, at least one lighting outlet controlled by a listed wall-mounted control device shall be installed in every habitable room. The wall-mounted control device shall be located near an entrance to the room on a wall. So, I'm just going to grab the 17 code too, because we technically didn't make a big change there. What we did in 210.70, we recognized the presence of wireless controllers, right? So we're not mandating it. We're saying we're giving you the option. So when I'm looking at the changes in 210.70 so I think Pierre might be confusing. Yeah, that's what I'm thinking, Ryan. I think you're confusing, Pierre. I think your assumption that you're making is that we're requiring it to be a wireless type of device, the smart devices, and that's not the case. It just says at least one lighting outlet controlled by a listed wall-mounted control device. What that does, a standard, very inexpensive, typically used up and down light switch is still a listed wall-mounted control device. So, but what this does is says if you installed, for example, yeah, let's take a look at the, if you installed, let's say you installed those, she's right over there, ALEXA light switch that doesn't have a toggle on it. The way the 210.70 read in the previous, it says in dwelling units, lighting outlets shall be installed in 813. At least one, we're in habitable rooms. At least one wall switch controlled lighting outlet shall be installed in every, so it would have to be a switch, and you would have to go back and see how things are listed to see if you could use some of these wireless, there's these wireless controllers that you can just stick on a wall and press a button on there, but there's no switch inside. It's wirelessly controlling the light and turning it on and off. So we're permitting the use of that, not requiring the use of that. So I think that's what you're doing, Pierre. I think you may have just misread that a little bit, which we all do. But all of the other changes in here, additional locations, we just replaced the switch with lighting outlet controlled by a listed wall-mounted control device. That's all we did in A. In B, now here's what we did do in C, which is a change, and I'm not sure if this is what he's talking about. And I know this was debated heavily at the table. In C, it says for all occupancies, for attics and underfloor spaces, utility rooms and basements, at least one lighting outlet containing a switch or controlled by a wall switch or listed wall-mounted control device shall be installed where these spaces are used for storage or contain equipment requiring servicing. So you go into a basement, you need one light switch to turn the lights on. Now it says in the 2020 code, a point of control shall be at each entry that permits access to the attic and underfloor space, utility room, or basement. Where a lighting outlet is installed for equipment requiring servicing, the lighting outlet shall be installed at or near the equipment. So what we did was we made a change, and the comment was made, look, I have two entrances to my basement. Technically, out at the bottom of the stairs that comes from the upstairs, I come down the stairs and I'll put a light switch there. The door that's coming in from the outside does not need a light switch because I've satisfied the code by putting one at the bottom of the stairs. So I come in from the outside and I come into a dark room. I'm not required to have a light switch there, and that's what you want to avoid. So, and another example, for example, I had in my last house, the first house I built, I had an attic. It was a Cape Cod type of home. And I had two, the upstairs, you came up the steps, you went to the right, you went to one bedroom, went to the left, you went to another bedroom. And in each bedroom, there was an attic way access, a set of pull down stairs. In the one bedroom, I pull down the stairs, I go up, and there's a light switch, which is required by the code, and that would turn the lights on for the attic. In the other room, I pull down the stairs and I go up, and there's no light switch. Why? Because they put the light switch over in the other stairs. So I would have to come down, go to the other stairs, pull those down, go up, turn the light on. And now remember, I can't get from one side to the other. There was there were support truss work and whatnot separating the two. I'd have to crawl like in between trusses to be able to get from one side to the other. That's why they put the stairs on the other side, but they only put one light switch. It met the code, the previous language. It would not meet 210.70c because I'd have to have a light switch for both entries to that space. So that was, and I know we debated that at thing, and I supported this because of my own frustrations in my attic. That was the primary place. I did not have a problem in my basement. I didn't have a walkout type of deal. I had a garage underneath my house, and I believe there was a light switch coming in from the garage. In fact, it was right when I came into the garage. It hit the garage lights and it hit the inside. So I didn't have any problems there, but I was very frustrated in that I had to pull those other stairs down. And then everybody at the table had examples of the exact same thing. So we did make that change, but I think that's a plus. And that's, I mean, I don't know that would be that expensive to be able to control. I don't know. I can't speak the cost, but in any case, I think it was an increase of safety. But that in 210.70, Pierre, I think you just made a misread there. All right, JW. Oh, you got a long one here, JW. I might paraphrase this one a little bit. This one was a week ago. And this was on, 240.87. I hope we can come up with a better solution for worker safety than this method. Not sure which method you're talking about. 240.87 has multiple methods. 240.87, if you have a circuit breaker, 1200 amps and above, you can do zone selective interlocking, differential relaying, energy reduction maintenance switch with a local status indicator, energy reducing active arc flash mitigation system. You can leverage instantaneous trip. You can do an leverage the instantaneous override in a circuit breaker, or you can have any other method that you want to do. So I'm not sure what you're talking about there, but maybe I'll learn more as I read on. Let me do this. I'm just gonna. All right, so I'm gonna scroll up here. My comment. There it is. While electrical safety has been of importance to me, and while I have always respected the concept of incorporating worker safety in design, I feel this section might be a bit problematic. Okay, I believe the requirements in 211.2.14 for an energy reduction maintenance switch was a good thing. The requirement in the 2011, having to prove reduction of arcing current. Oh, okay, JW. All right. So here was the issue there. Here's the issue. And JW, I would not, here's my opinion. So let me just tell you, let me just talk to what you said, proving reduction of arcing current. There were submissions that said that you could install the product, say it's zone selective interlocking, and the arcing current could be lower than the pickup point for the short time delay set points, and not do anything. You could put an arc reduction maintenance switch on and it won't do anything. You could do differential relaying and it won't do anything. And what did you gain out of it? So it was hard to argue against saying you should make sure that it does what you say it does. But to your point, JW, if you look at 230.95, okay, what does 230.95 tell us? 230.95 says that we need to put ground fault protection of equipment on any circuit breaker or fuse 1000 amps and above. It tells us that we can't have a setting greater than 1200 amps, but it doesn't say in 23095 that it has to respond to ground fault current. You don't have to calculate ground fault current, compare it with the ground fault protection of equipment settings and say it does something. You don't have to do that at all because there's nothing in 23095. Now, you do have to performance test it to make sure it works, but you don't have to prove that it will respond to ground fault current. So, I think your comment is I still I don't know that I disagree with you. I can't say I totally agree with you. I think that 24087 needs a little bit more love. But that was the discussion points. And I know in my head, I was thinking 23095, we don't have to prove that over there. Why all of a sudden we have to prove it in 24087? But 24087 is about worker safety. So I think that comparison and that analysis should be done. And I know you have a lot of dialogue here, and you probably bring up use of higher resistance and conductor terminations as they age. So your points are that the arcing currents are going to probably change. And then you made a statement here about the main breakers located. They have a breaker of 12. What we see next, people using the 6-switch rule to keep the disconnects or breakers under 1200 amps. Absolutely. I mean, they do that now for ground fault. People don't want to put ground fault on 1000 amps and above. So what do? 600 amps, right? They'll split that service specifically to get out of the 1000 amps and above to put GFPE. Now, what we are doing, we're lowering in the 2023 cycle, we're taking GFPE down to 800 amps. You'll notice in 110 for working space, we went from a working space driven off of a 1200 amp service device to, if you add up those devices and they're equal to 1200 amps, now you need to have that extra door. So they're making changes there, realizing that what people are doing, to your point, JW. So 24087 is moving down to 1000 amps, and we almost passed down to 800 amps during our code cycle, but I think it was Alan Manchi and another on the panel pushed back and said, we can go for that, but we need a delay. So I don't disagree with you. That's what, people will change their designs, and it's unfortunate. We could specify 247 to what extent supply conductor being based on the speed is based on the bolted fault current of the transformer. Yeah, so I agree with you that it can be difficult to determine, and that's why the qualified person should be doing an analysis to determine the available fault current and the arcing current, come up with the set points. And remember, 24087 doesn't say the minimum arcing current or maximum arcing current. It just says arcing current. So if you're familiar with 1584, I have to calculate two values. Which one of those am I going to use? If I really wanted to be a jerk, I could say, hey, I'm going to use the maximum arcing current because that gets me out of 24087, and the minimum arcing current makes me put an arc reduction technology in. Is that the way you really want to do business, right? Is that what you're, if something happens and you were on a stand and the lawyer looks at you and says, which value did you use, Mr. Dimitrovich? Well, I used the larger one. Why didn't you use the lower one? Because that showed that the arc reduction technology wouldn't work, and this guy got hurt. Well, it's cost me. It would make me add cost to the installation. Oh, okay. Well, you're going to pay more for his hospital bills. So you never know how that stuff is going to go down. So, any arc flash calculation, JW, is liability, right? I mean, think about it. If you're going to do an arc flash calculation and you are going to label a piece of equipment, you've got to do it right. And yeah, there's there is the challenge there. So I think when you run your calculations, if you're using IEEE 1584 the way it is, and this is service entrance, well, it's not service entrance equipment. It's any circuit breaker now 1,000 amps and above for the 2023 code cycle. So yeah, you've got to do your homework. You're gonna have to. It's gonna be a challenge. Hell, Teresi, good to see you, buddy. Do you still need to follow 24087 when the circuit breaker is set on lock rotor or SCCR? Al, I'm not sure if I understand that one. Do you still have to follow 24087? You have to follow 24087. I think I know what you're talking about. I'm not sure if I know what you're talking about. Circuit breaker is set on locked rotor. So if you're thinking about a fire pump, 24087, there's no exceptions in here for fire pumps. So no, I mean, here's the thing, Al. What I would say is when you look at 24087 and you want to know where does it apply, you would say if you have a circuit breaker that is 1200 amps rated, 1200 amps and above, or can be adjusted to. So how do we know about the rating? We go back to 240.6. Yep, 240.6 gives us the standard ampere ratings. And even if I have the locked covered on there, if I can adjust it up, regardless of whether or not it's locked, if it's a 1200 amp frame set at 600 amps and it's locked cover, you can technically say it's rated for 600 amps. But 24087 says or can be adjusted. So if you can adjust that, then you still have to apply 24087. And it doesn't, there's nothing else. So if it's, I don't care if it's a DC breaker, an AC breaker, I don't care if it's set for locked rotor amps, I don't care if it's set for inrush currents on transformers, I don't care how you set it. If it can be adjusted to 1200 amps, you need to have 24087. It could be on a fire pump controller. It could be in a life safety system. There's no exceptions for 24087. Yeah, no exceptions. I hope that helps, Al. And if I didn't get that question correct, about 100% rated breakers, if I buy a 2000 amp frame 80% breaker and turn long time down to 1600 amps, could I use in place of a 1000 amp? Oh, John Walters, hold on. I'm going to have to, I'm going to get back to you, but I just want to make sure I answer. I'm going to go in order here. That's a new one. So let me, and I'll get to it. It's only 12:21. I got till 1 o'clock. So give me a second here. I want to get to Matthew Hermison, who 6 days ago asked a question. Oh, I love this. You missed the point massively. Boy, did I screw that one up. Which one is this one on? How did I screw this one up? I missed his point. I didn't just miss his point. I missed his point massively. That is scary. Okay. Let's take a look. Where is the you missed my point massively? There it is, Matthew Hermison. Okay. This was my response to his question. So let me go find his original question. And before I read, you know what? I've already answered it. So I got to go back up. Let's see what he says. Let's see how I screwed this one up. The discussion was about energy codes and energy efficiency. The most energy efficient HVAC condensing units are VRF, or variable refrigerant flow systems. The compressor is driven by a VFD, or a variable frequency drive, or freak drive. I've never heard of a freak drive. Anyway, these systems have shown upwards of 50% savings in energy usage. Amen, brother. They have. Currently, most VFDs are not designed to operate with Class A GFCI. I disagree with that. You say, here's the thing. When you start using words like most or all, where's your numbers? Because I can tell you, we've done a lot of testing. There are a lot of HVAC products out there that work with GFCIs, that work within those constraints. There are some manufacturers. Now, if you may have one manufacturer that says, I could tell you there's probably at least one manufacturer that I'm aware of that I could say all of their VFDs don't, and not because of high frequency, because they are using the equipment grounding conductor as a load return. They're actually putting a load between hot and ground because there's no neutral there. It's a 60 hertz thing. So, and there's nothing in the UL standards to say you can't use that equipment grounding conductor as a neutral for a neutral load. There's no test in there for it. And they're trying to change that right now. So I would say it has nothing to do with the VFD. In fact, we found some lower efficiency units that are using the equipment grounding conductor as a current path. So there's, you got to just be careful of the using the words most and or all and things like that. So, and I say some, I mean, I'm not going to say all, I'm going to say we found some installations, some solutions that are intentionally using the equipment grounding conductor as a, for 120 volt type of application within that unit because they don't have a neutral there. And again, that's a 60 hertz, that's a 60 hertz thing. And you can say, well, you won't have a problem if you just would have, you can, but that violates Article 250. Okay, Article 250 on grounding and bonding tells us you can't have objectionable currents on the equipment grounding conductor. So objectionable currents needs to be looked for regardless of the application. So, and we have a body count associated with it. So you got to be careful there. And this is the reason the more energy efficient variable refrigerant flow systems cannot operate with a GFCI device upstream. In the Chicago death that triggered an addition of 210.8F to 220AC, the equipment grounding conductor used was a raceway type, and the whip had reportedly broken 2 sections. Remember that this was in Chicago, where, most of those are in raceways, right? However, the ungrounded conductors were still intact. Thus, there was no equipment grounding conductor in working order to protect against the ground faults. Had there been a wire type equipment grounding conductor installed, the odds that the OCPD would have opened long before the victim entered the yard. I can't say it would have. I can't say it wouldn't have. And that's my other comment is if I had ground fault protection of equipment and not even GFCI on there, I would have cleared that long before somebody would have touched it as well. You could very well be right there. Just adding a GFCI device upstream absolutely does not mean that the device will ever be tested, let alone work as needed when it might need to operate. Nothing's guaranteed in life. Absolutely right. But if the wire type equipment grounding conductor was damaged, odds are, but you can't guarantee it either, right? You say odds are, right? And I could say the same thing, that the odds are the GFCI will do the job. Odds are the GFPE, if you had it on there, it would have done the job. Odds are, if you had the equipment grounding conductor there, it may have done the job. So, I mean, odds. I mean, if you're a betting man, sure. The results of 210, we now have people in the warmer climates who have their new condensing units, GFCI breakers opening and depriving the occupants of cooling during heat waves. Well, so I think that's why and NEMA and others supported the TIA that I believe would have addressed this. We also supported the TIA a while ago, but then the Standards Council rejected that from an emergency and nature perspective. So in any case, I can't speak, how they would handle the GFCI from how many people would die if they didn't have HVAC. I mean, I think it's a proven point that HVAC is important in many cases. Would be more robust and thus more reliable. Remember, though, our equipment grounding conductor is not GFCI protection. So I can't go with just say, bring an equipment grounding conductor out there and leave it to be. I think if you wanted to have a debate on whether you should have GFCI or GFPE, I'm open to that discussion personally. But to just sit down and say GFCI, you don't need GFCI, it's more reliable than GFCI, I completely disagree with you there. Sorry. Yes, if the ground fault had high enough resistance, a GFCI device might help. Yeah, again, odds are, right? But a properly installed wire type equipment grounding conductor in a dwelling unit would rarely exceed 1 or maybe 2 ohms, right? Again, these conversations, and this is why when we sit at the table, we all have our opinions, and I can respect your opinion. But you're using words like probably, odds are, and I'll use the same words, probably, odds are, and we haven't gained any ground together yet. So I think the crux of this issue has to be solved in the standards, and the HVAC manufacturers have to make sure they just simply don't violate Article 250 for objectionable currents in the equipment grounding conductor. Don't use that equipment grounding conductor, and I think that this problem would go away. So hopefully the TIA will be successful, and we'll give them a few years to get some stuff in order, and then get back onto the queue, right? So hoping that happens, Matthew. I'm hoping. All right, brother. Okay. Let me just take a look, and I think I've got one more here. Yep, JW. On my comment minute 46 in your video, I'm speaking about things like very large customer-owned generation step-up substations, maybe 50 MVA, 250 MVA, that have secondary voltages of 35 kV and primary voltages at the higher transmission level voltages. These aren't listed assemblies or just a combination of transformer and 480 volt gear. They are separate components of things like, okay, so I think this was when you were talking about the lower voltage stuff. Here's what I'm going to say about that. I think that you sound very knowledgeable on medium voltage equipment, more knowledgeable probably than I am on medium voltage installations and all those different components. And is there an opportunity? Are there things missing in the National Electrical Code? I'm sure there are. And the effort that's moving forward is going to put some attention on medium voltage. So 250.94, you say many grounding studies conclude to prohibit things like metallic shields of fiber. As a result, the serving internet utility is required to serve the premises with a non-metallic means. We have no metallic shield in the fiber, thus no need to interbond. Yet one would be required to add this thing that forever tempts people to use it. NEC grounding and bonding rules for station service transformer conflict with the NESC, yeah. Yep. The backfeed power warning labels required by Article 490 will require one to pepper a station with backfeed power warning labels that would so prevalent as to be ignored. Like I'm mentioning, though, so you're pointing out some of there are deficiencies. You're pointing out deficiencies in the National Electrical Code and that need to be addressed. And I think you were talking about creating a new article for substations and these applications. Yeah, I mean. I think that would be great. Now, I don't think we have an opportunity this cycle, but I would suggest you reach out to maybe Larry Ayer, the Correlating Committee Chair, or Robert Osborne, who's chairing the medium voltage equipment, medium voltage applications, and you could probably get to him through Jeff Sargent. I reach out to Jeff Sargent and say, hey, if you want to get involved with that, if you have ideas, you might be able to have your voice heard in that opinion, in that way. So I think it's a good idea. All right, John Waters. Hopefully that helps, JW, and I really appreciate the dialogue on that. Really do. All right, so let's get to, I'm going to close this. Don't save. 1232. I have a question about 100% rated breakers. If I buy a 2000 amp frame 80% breaker and turn long time down to 1600 amps, or even 1600 amps turn down to 1200 amps, could I use this in place of a 100% rated breaker? Well, let's think about this. When you think about a 100% rated circuit breaker, what are we doing? How do we get there? The first thing, what decides you're into a 100% rated system is when you do your load calculation. You take your loads that are non-continuous at 100%, and if you take your continuous loads, 4 hours or more, 3 hours or more, then continuous loads, I believe, is 3 hours, then you add that in at 100% and you don't do 1.25. And then you're going to come up with a you're going to come up with, and it is 3 hours, then you're going to come up with a number for an ampacity, and you're going to protect it at that size. And what you're saying is if you took a breaker that was a higher ampere rating and adjusted it down to 80%, could you do that? Well, I would argue, John, that you don't have an 80% rated application if you do that. You don't have a 100% rated application if you do that. Because, remember, I can get there two different ways. I can take all of my load currents and let's say I don't even have to do the math. Let's just say that you are calculating it out and you didn't add the 1.25 in when you calculated all your loads, and they're all continuous loads. If you took and increased the size of the circuit breaker by 1.25, then you've and protected the conductor with that, even if you've adjusted it down, you're still at 80% on the breaker. Right? Yeah. You're still at 80%. So whether you apply the 1.25 at the load or you apply it up at the ampere rating of the breaker, the difference is going to be the conductor. The conductor that you're picking. You're not picking a larger conductor in that application. So if you're not picking a larger conductor, and I need copper, right? Boy, John, my gut's telling me that you are taking into account, because you've increased the size of the breaker. You're putting a larger breaker than what you would have bought in a 100% rated. So if I had a 100% rated 100 amp breaker, yeah, I could use a 100 amp breaker, 100 amps worth of conductor. That's 100% rated. If I used 100 amps worth of conductor, but I used a 125 amp breaker, I'd put a larger breaker in, and I'm using the conductor at its ampacity. You know what I'm going to do, John? I'm going to take this one, and I'm going to think about this one a little bit more, and I'm going to run some examples for next Friday, for our next Friday session. So I'm going to, I'm just going to email this to myself, because I don't want to answer it incorrectly. Question for Friday. I'll put that in. And this is John Waters. John Waters. So I'm going to say, check me out Friday, because the only thing that you're not doing is increasing this. So if I had, for example, if it was 100 amps worth of continuous load, I would size my conductor for 125 amps, which would mean my conductor would be larger. And then I could put that on a 125 amp circuit breaker. I couldn't put it on a larger circuit breaker because I need to protect it at its ampacity. So I'd have a 125 amp breaker with a 125 amps worth of conductor. So the question would be, if I had a 125 amp frame breaker adjusted down to 100 amps to protect a conductor at its ampacity, which, as long as the conductor, remember, a conductor is a conductor. If I go to the tables, if I do a 100%, can say these loads are going to be on all the time, and I go to 310.15, I go to 310.15, I know that let's say 75 degrees C, a number 3 can handle 100 amps worth of conductor. It can handle 100 amps worth of conductor all day and night. It doesn't matter. Then I would put a 100 amp breaker on it. But if I took if I took a 125 amp breaker or a 200 amp breaker and adjusted it down to 100 amps, I'm okay. And protect that conductor at 100 amps. So, but I've increased the size of my breaker, right? So I'm no longer using a 100 amp breaker at 100 amps continuous. Now I'm generating heat. My conductor is not large enough. I'd have to increase the size of the conductor by 1.25 to be able to give me the copper to take off the heat. But that's not what I'm doing. I'm not using a 100 amp breaker to protect 100 amp worth of load all the time. I'm using a 125 amp breaker to protect a 125 amp conductor, which is only carrying 100 amps. But that conductor can carry 125 amps all day long. The only reason I'm upsizing that conductor is because the breaker needs the additional copper to take the heat off. But if I use a larger breaker, it's larger lugs, there's larger everything in there, and I put a smaller conductor on it. And as long as I'm protecting that conductor at its ampacity, I can't perceive the problem right now, but I'll do my homework and make sure that that's Kovacevic. But I wouldn't call it a 100% rated application either, right? Because it's not a 100% rated breaker that you need. You have a larger breaker than what you need, and you're adjusting it down. I will do my homework on that one, John. Good question, though. Good question. I think the number of variables in calculating an arc through the air, we talked about that one. We got Robert from Ophel. The answer is not 24087. It's about overcurrent. Is no, 24087 is about overcurrent protection. Answer is no, 24087 is about overcurrent protection. Let's take a look at your, do you still need to follow 24087 when the circuit breaker is set on locked rotor or SCCR? Yes. 24087 is not about overcurrent protection. 24087 is about arc flash reduction. So you still need to have 24087. 24087 is not about overcurrent protection. It's not about protecting the conductor. It is about arc flash reduction. That's why we compare the arcing currents to ensure we're reducing arc flash. There's no exceptions that says anything about if you sized it for SCCR is not overcurrent protection. SCCR is equipment protection, and SCCR is about the ability of a piece of equipment to withstand letting current pass through it. That's not related to arc flash. And you brought up SCCR, and then you brought up locked rotor. I mean, if my circuit breaker, well, let's talk selective coordination. Selective coordination. If I selectively coordinate two breakers together, the upstream breaker is going to hold its contacts closed for the maximum available voltage short circuit current, which will be much more than any locked rotor current that you have on a motor. I still need to apply 24087. In fact, that's where you really should have 24087, regardless of the size of the overcurrent protected device. So no, I don't necessarily agree with that. You would still need to follow 24087 if you size that breaker for locked rotor, if you size the breaker to provide short circuit current ratings, if you size the breaker for selective coordination. It doesn't matter. You still need 24087. There's no exceptions in there. Robert from Omaha, you do the best you can. Document what was done and what was not done, if possible. Make an effort is one thing. Totally ignoring safety is quite another thing. I would agree with that statement. I think more research and documents to allow a non-engineer to determine with transformer impedance and conductor properties if the instantaneous override can be relied on would be helpful. I agree, JW, and I think I'll tell you what we did do. Bussmann is helping. We haven't done anything like this for Bussmann arcing current calculator. So the Busman people did some stuff for us. Let me do this. Me and PowerPoint. Yes, there we go. If you go to arkingcurrentcalculator.busman.com, you'll get to this website. And what we've done here is we say, nope, that's not the right one. Scratch that. That's not the right one. arc.busman.com. This is it. Goodness gracious. Okay, so in this one here, we leverage the latest version of 1584. And I'm going to put a link to this. arc.busman.com, Control C. I'm going to put it here, Control V, arc.busman.com. And I think I've got to go to, I've got to go over here to bada bing, bada boom. Where am I? Okay, so I'm going to come over to my live session over here, and I'm going to post it in LinkedIn, because this won't do that for me. All right, so I posted it in my LinkedIn, and I posted it over here in, what do you call this? YouTube and Restream.io. All right, so let's talk about this. So if I have a panel board, so we got gap, and it tells you if it's a cable junction box, and this is right out of 1584. Say a panel board would be 25 millimeter gap, and that's the bus gaps. Electrical configuration, VCB, VCBB, HCB. Those are the only three I'm putting in there, primarily because, probably not, the others are probably are more associated with utilities, outside equipment. So VCB, vertical bus, I think worst case for a panel board would be VCBB. Voltage, 480 volts, we'll say. You enter your bolted fault current in kiloamps. We'll say 65,000 amps. You select your fuse rating. Remember, 24067 goes from 1200 amps to 2500 amps, and you say it's a, I don't know, let's say it's a 1200 amp fuse. You do calculate, and it tells you what your maximum and minimum arcing currents are coming from the utility at that service, or the upstream, up from the upstream. Based upon the fault current that you put in, you would have to figure out what is your minimum fault current. That's you want the fault current that does not have the motor contribution from upstream. KRPC 1200 passes and KTU 1200 passes, so you don't need arc reduction. And what that's telling you is that you have a clearing time of 0.07 seconds or faster at the lowest arcing current. We picked the lowest arcing current to do that evaluation. So hopefully, to your point, JW, I think I'm hoping that this might help those in the trade and in the industry and inspectors, et cetera, to come up with an evaluation and calculating arcing currents and stuff like that. All you have to be able to do is come up with that minimum minimum bolted fault current value. So I gotta make sure. Okay, there we go. All right. On circuit, okay, so let me go down up here. I think the more research and documents allow non-engineer. Close odds are works only for hand grenades and horseshoes. There you go. Ryan Jackson, the overcurrent device must be sized to carry the continuous load. Adjusting it to less than that violates. Yeah, Ryan, but remember, he's taking a 1200 amp breaker and adjusting it lower to be able to carry to protect the conductor at its ampacity. So if I have 100 amps worth of ampacity and I have 100 amps of load, continuous load, and I have it on a 1200 amp breaker and I adjust it down to 100, I'm protecting that conductor at its ampacity. So I have that 1200 amp breaker can carry 1200 amps. And I adjust it down to, to something lower. I could carry up to 1200 amps on that, and I'm actually carrying something less, 80% less. Right? So I'm adjusting the long time pickup down. So the overcurrent device can handle more than what I'm putting on it. I put a smaller conductor and I adjust it down so the breaker physically, if I adjusted it always up to 1200 amps, I can carry 1200 amps worth of current, but I'm not. I'm carrying 80% of that on a conductor, and that's at 100%. So I really got to think about that one. I really got to think about that one. L says, on circuit breaker that provides overcurrent protection. Okay, so on a circuit breaker, so let's see, he's still arguing 24087. 24087, where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1200 amps or higher. Right. So put it this way, that language is in 23095. So if you had a circuit breaker sized for the locked rotor and SCCR, do you not put GFPE at 1000 amps and above? So in New York, or not New York, in your jurisdiction, do you not put GFPE on a 1000 amp breaker and above because it's sized for locked rotor amps? That would be a question there. So if you do the same thing there, then I think we need to talk. But the same exact language, which is in 23095, we've got it over here in 24087. So whatever you do on 23095, you better be doing for 24087. And I don't agree that just because it says it's installed in a breaker is rated or can be adjusted. I'm not sure where you're going with that one, JW. But turning a breaker down and sealing it to make it allowed doesn't necessarily reduce the additional heating on the trip unit if it operates at 100% of the setting. I don't disagree with you there. What I'd have to really do is look at the conductor size and the amount of current. So I really got to think about that one. That's a good question, though. Whatever they discover should be added to the NEC so it can be considered safe harbor. JW, amen. Read the main rule for the overcurrent device. In my view, is this type circuit breakers are not providing overload protection, therefore not in section 24087. So where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted. Installed in a circuit breaker. The actual overcurrent device installed in a circuit breaker is rated or can be adjusted. So you don't put GFPE on those either then, do you? L. So 23095. Let's take a look at 23095. Ground fault protection of equipment shall be provided for solidly grounded electric ground, but not exceeding 100 volts face to face for each service disconnecting. More, the ground conductor for the solid wire system shall be connected directly. The rating of the service disconnect shall be considered to be the rating of the largest fuse that can be installed or the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted. So you don't do that. I don't think you can go there. It's still an overcurrent device, even if you're not using it. It doesn't say where the actual overcurrent device installed in a circuit breaker, when used, is there an overcurrent device installed in that circuit breaker? I don't care if you use it or not. If you had an instantaneous only, like a motor circuit protector, then I could say, okay, that's not an overcurrent protective device. But the fact that you're using an overcurrent protected device higher than the locked rotor amps, I don't care. I don't care how you use it. The fact that you're using it and it doesn't say when the overcurrent protection is used. It just says which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted. It doesn't say how you're using it or how you're setting it. If it's an overcurrent protection in there, you're in 24087, just like 23095. And that's my opinion. I don't care if it's not providing overload protection. I don't care. It doesn't say that it has to. It just says it has to have an overcurrent device installed in the circuit breaker. It doesn't say you have to use overcurrent. It doesn't say it has to be set any particular setting. It just says if it's 1200 amps or higher. But Bussmann requires indemnity, of course, should add to the NEC to make safe harbor. Too many variables to wrangle. Yep. That software is only for 24067. Yeah, it's only for 24067. It's not for 24087. But I mean, you could calculate the arcing currents and compare that to trip curves, and then, you know, put it in a drawing, stamp it with your stamp, and on your way. It might be manufacturer specific on the trip current thing. Yes, it might be. It will be. Every manufacturer's trip curves are going to be different. So you've got to compare the arcing currents, the minimum arcing current, with the clearing time of whatever manufacturer's overcurrent device. Daryl Heel in the house. Is the 125% requirement to prevent damage to OCPD or equipment or to prevent nuisance tripping? The 125% is to align with how the product is tested in an assembly. So when we add the 125% in on a conductor, we increase the conductor size because I need that copper to help pull heat off of the device. So if I, you know, if I have a 100 amp circuit breaker, if I load it up to 100 amps, then I'm using that circuit breaker at 100% of its rating. That's not how we test it unless I list it as a 100% rated breaker. And in that case, I might have to have a 100% rated breaker installed in a panel board that might have copper density. So if I go to, I have a doodar. I've got a technical presentation on this. Basics, 100% rated. Oh, doodar day. All right, so let's take a look at this. Let's take a look. Let's take a look. All right, so 80% rated breaker, 100%. Here we go. Code reference 210.20. I'm just going to flip down through some slides here. This is out of how we test the breaker in UL 489. 100% rated circuit breaker marked for use 100% is in the smallest enclosure. The JW, it's both the assembly and the breaker. So the breaker and the assembly go together. So look at how we test this device. We have a 100% rated circuit breaker marked for use at 100% rated. It has to be tested in the smallest enclosure within which it is intended to be used, or in open air as part of an X sequence followed by a second test with the smallest enclosure. 100% rated circuit breakers shall be tested in the smallest enclosure or cubicle. So space, it's about temperature. And they say the temperature rises where connections are made to external bus bars when the bus bars are used, or on a wiring terminal at a point in which the insulation of a wire is brought up as in actual service when tested with insulated wire shall not exceed 108. So they're looking at the temperature rise on certain parts inside the enclosure, and they're looking at temperature rise on certain parts inside the enclosure and also in the enclosure itself. So they're measuring temperature inside. For the 100% rated test, a circuit breaker shall be connected with copper bus bars if the circuit breaker is intended for use with both bus bars and wiring terminals. Unless the circuit breaker is marked to indicate otherwise, the bus bars shall have a cross section. So they're telling you the size of the bus bars, and it has to be copper. Where does it say copper? Have a cross section for ratings. A circuit breaker shall be connected with copper bus bars. So it has to be copper. So if you have an enclosure that has a aluminum bus, you are not going to have a 100% rated enclosure because it's all about heat. So a circuit breaker having a frame size of 250 or greater or a multi-pole type and intended for continuous operation shall be marked suitable for continuous operation, 100% of rating, only if used in a circuit breaker enclosure. And so they specify the enclosure or in a cubicle space. Okay, so they're specifying this. Remember, we're talking, this is very integrated with the enclosure and the copper and all of that stuff that you have going on inside of there. We know current rating. All right, so this is out of the UL White Book. Unless otherwise marked for continuous 100% of current rating, a circuit breaker is intended for use at no more than 80% of its rated current, wherein normal operation and load. So here's my point. If I have remember what he said, here's what he said. He said up above, and it was a good question. He said, if I buy a 2000 amp frame, 80% breaker, and turn the long time down to 1600 amps, so that's your 80%. So a circuit breaker is rated to carry 80% of its rated. So if I take that 2000 amp breaker, turn it down to 1600, which is at 80%, now that breaker is, I can use a conductor, 1600 amps worth of conductor can carry 1600 amps. I'm perfectly fine. I don't need 100% rated on anything. I can use that conductor at 1600 amps because this breaker can carry 2000 amps, 80% of that. And I've set the setting for that. So that's my issue. I think I don't need that to be 100% rated for this reason right here. You know, it's what 80% of its rating. So that 2000 amps is 1600 amps is 80% of the rating of that 2000 amp breaker. It's a 2000 amp frame breaker. So I can carry 80% continuously. So if I do my calculations and everything's at I have a continuous loads, continuous loads. If I have 1600 amps of continuous loads, then I put it on a 2000 amp breaker and I adjust it, and I put 1600 amps worth of conductor and I adjust it down to 1600 amps. I don't see what the issue is. I'm perfectly fine. It's an 80% rated breaker. You're using it at 80% of its rating. That's where my head's at. And the more I think about it, that's where I'm at. I mean, I think you're perfectly fine in that application. And when you look at, so when you look at this, so these are like out of our catalog. You've got, this is our catalog, and it says there's my 100% rated breakers are 3, which would be the CDK, and it would be the CHKD. And what does it say here? So not all of these are 100% rated. And this one is a panel board. So what this says is 100% rated circuit breakers require copper bus, not available in type 12, 4, and 4X enclosures. So not every enclosure that you get, not every assembly is going to be able to handle a 100% rated breaker because it's got to have copper bus. And it might have to be a special type of copper. Take a look at this one. Right behind me here, it says 100% rated breaker requires copper bus. K and N frame breakers require density rated copper bus, not available in type 12, 4, and 4X enclosures. So this is telling me that I need density rated copper bus. That's a little different. I think the caution is if there's other breakers in the assembly rated 80%, well, these are all rated 80%. Yeah, so 215A1 exception requires the entire assembly. You're correct. The entire assembly needs to be rated 100% rated. But in what his question was, he's using a 2000 amp breaker, adjusting it down 20% to 80% of that rating and using it as an 80% rated breaker. You're perfectly fine. I don't have a problem with that. I can't see any issues there. So anyway, I'm up on my hour. I am 2 minutes overdue for my call. And oh boy, I don't know what my number is. Anyway, I got to drop off. So thanks everybody. Thanks for tuning in. Hopefully you're getting some out of these Q&A Fridays. I know I'm loving the dialogue. So thanks for joining in. I am going to hop off and try to figure out the number that I need to dial in. So thank you everybody. What is the number? Oh no, it's up here. He sent it to me yesterday, or he sent it to me last week. All right, so I'm going to sign off. Thanks. I'm multitasking. Much more interesting than I originally thought. Yeah, it is, Ryan. That was a really good question. Okay, everybody, thanks for dialing in. I have to really jump off. I'm going to get in trouble. So take care, stay safe, please, 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 please. Stay healthy, and we'll see you next week. Next week I'm in, so I should be doing Tuesdays and Thursday and Friday. No, Tuesday is IAEI. We're going to have an IAEI live session on the IAEI. So don't forget that one, IAEI meeting. We're going to have a live IAEI session, so I'm going live on Tuesday at noon. But I'll probably still do it 5 o'clock too. But anyway, take care, stay safe, and please stay healthy. Oh my goodness, I got to get out of here.